Good afternoon, everybody. Thank you for attending this presentation today. My name is Tanya, and I would like to share with you what we are working on at Big Data Analytics Center at United Arab Emirates University. One of our research topics is related to the patterns of normal or accelerated aging. And today, I would like to talk about early marker of dementia using deep learning technique. So let's get started. Our agenda for today is as follows. So we'll start from the motivation, why we decided to work on this topic. Then we'll move to the introduction and literature review. We'll formulate our objectives and methodology of the study, the data preprocessing techniques we used, and an overview of the proposed method. Then we'll discuss our results and finally conclude and highlight of the future direction. The worldwide population faces the problems of aging and age-related diseases. For example, in the United Arab Emirates, the life expectancy increased by 4 years in the last 20 years. So the importance of studies covering neurodegenerative disorders is high, and many researchers are attracted by this topic. Neurodegenerative disorders are incurable conditions that result in neuronal loss and progressive deterioration, that is dementia. Dementia is characterized by devolution in memory, judgment, thinking, orientation in the space, and ability to perform everyday tasks. It's one of the major causes of disability among older people worldwide, and Alzheimer's disease is the most common form of dementia. Structural signs of dementia appear earlier than functional. So by the time that a person begins to experience the symptoms of the disease, its condition is already well established in the brain. Brain imaging, though, may serve as a subtle marker of dementia. However, the diagnostics of a disease is most commonly done with the help of cognitive tests. This task is challenging because it's time-consuming and there is no standardized test. So why don't we use both a structure and function and use that association between structure and function to improve the diagnostics of dementia? AI, or machine learning and deep learning techniques, may help to identify patterns that are related to the changes specific to neurodegenerative disorders. As we mentioned earlier, dementia is associated with structural and functional changes. So it should be modeled with a combination of neuroimaging as well as neurophysiology. Let's take a look what is happening in the literature. Many researchers are trying to address the issue of predicting the diagnosis from structural MRI images. However, the clinical value of such models is limited because mostly researchers are trying to predict the diagnosis from a cognitively preserved and cognitively retarded population jointly, as well as they are not using a functional part of the association. Here, we present a different approach. We would like to look at the patterns of age-related changes specific for the normal aging, and then identify the gap between normal aging and accelerated one. Our objective here is to work out the screening tool for dementia by testing if the gap between actual and predicted cognitive performance from structural images can serve as a marker of cognitive deterioration. By addressing this objective, we are formulating several tasks, specifically to conduct exploratory analysis on the functional features for the study cohort, then to calculate the predicted cognitive gap from MRI images with a convolutional neural network-based regression model, then to justify the predicted cognitive gap as a screening tool for dementia, and finally to provide a comparative analysis of different cognitive tests predicted from structural features. Let's get started from the data. So here we use a 1,400 cases acquired from the ADNI database, which contains some pre-processed T1-weighted images, some clinical information on the final diagnosis, demographic data such as age, gender, ethnicity, morphometric data such as volumes of few brain areas, and then cognitive assessment data, which is the results of cognitive tests. The acquired structural T1-weighted images will be processed using few steps, such as we started from the registering all the T1-weighted images to MNI 152 space. Then we conducted additional bias field correction. Then we moved to the normalization and normalized the intensity of voxels by scaling them to the stored normal distribution parameters. Finally, we extracted non-brain tissues from the images and performed background removal and cropped the images within the limits of the brain tissue. To reduce the computational complexity of the problem, we decided to convert our 3D pre-processed T1-weighted images to 2D by applying the Formula 2 and Formula 3. So we created 3 data sets from axial, coronal, and sagittal averaged brain images. Created data sets were individually fed to the proposed convolutional neural network-based regression model. This model was trained on the cognitively preserved population and then tested on MCI and Alzheimer's disease cohorts. We used 20% of training data for validation purposes with 5-fold cross-validation technique. We used cognitive test results as an output of the proposed model. Let us move to the results and discussion part. Our first objective was to conduct the exploratory analysis of functional and structural data. As we can see from the table number 2, there are significant differences between cohorts in terms of structural and functional features. Meanwhile, cognitively preserved and MCI and dementia groups are not significantly different in terms of age. The second objective was to calculate the predicted cognitive gap from structural images using CNN model. Table 3 illustrates the performance of our CNN model fed with single or multimodal 2D images. To assess the predictive potential of the applied model, we move to the objective number 3. Justify the predicted cognitive gap as a screening tool for dementia. To perform this task, we applied a conventional machine learning model to the predicted cognitive gap values and tried to prognosticate the diagnosis of a disease. From the table number 4, we can see that proposed predicted cognitive gap can accurately segregate a cognitively preserved population and population with MCI or dementia. Finally, we decided to provide a comparative analysis of different tests with regard to the predictive potential of the applied models. Table number 5 shows the performance of the random forest-based classification model to prognosticate the diagnosis of dementia out of PCG values. The top listed tests in terms of the predictive accuracy of the employed random forest-based classification model are Alzheimer's disease assessment scale test and mini-mental scale examination test. These two tests are primary cognitive assessments required in all recent FDA clinical drugs and trials for Alzheimer's disease in the U.S. From the conducted experimental work, we can conclude that the predicted cognitive gap can accurately segregate healthy subjects from the demented ones, and it may serve as a screening tool for dementia. For our future research, we would like to check if our approach can be applied to different types of dementia. Thank you very much for your attention. Now the floor is yours for the questions, comments, and suggestions. They are highly appreciated.